Okay, so this chapter covers a lot of stuff. There's a lot of different things I can ask, but one of them we talk about imaginary, and we know a square root of a negative is not a real number. It's going to have an imaginary. So in this case, square root of 25 is 5, imaginary, 5i. This one's a little bit harder. We know there's going to be an I on there, but that 98 needs to get broken down. And so the best thing that you can do is think about numbers that we know the square roots of. Square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, and so on and so on. You should just kind of know these, and you can go out as far as you need to. Usually by the time you get to like 100, that's pretty much all you need. It could go higher than that, but what you want to do is you want to split this 98 into something that you know the square root of. And I know that 98 is 49 times 2. And why that's useful to me is because I know the square root of 49 is 7. And so there'd be a 7, and there'd be an I, and there'd be a square root of 2. That would be your answer. That would be your simplified answer. Now the next one kind of extends it even further, but we have to do the same thing with that square root of 54. So square root of negative 54, we know there's an I on it, and we can break down the 54 into, I guess it would be 9 and 6. Square root of 9, square root of 6. That's the best way to do it because the square root of 9 is 3. So this problem, I would just kind of rewrite that square root, negative 6 plus 3i square root of 6 over 3. And then we can reduce our fraction. I think of it as splitting the fraction. You've got two different fractions if you split. Negative 6 over 3 plus 3i squared of 6 over 3. And you can reduce both of those fractions, negative 2 plus I squared of 6. Next one, students really struggle with this one. This is one of the most commonly missed questions in this chapter. You've got an I on the bottom of a fraction. In order to deal with that, we're going to multiply by a special form of 1. We're going to use what's called the conjugate. And so you look at the bottom, and whatever this is, you're going to write the opposite. It's kind of a coincidence that it matches what's on the top. The top could be anything. I don't really care about the top. But what I've just done is I've multiplied by a very special form of 1. Multiplying by 1 doesn't change the value. Now you just need to do a whole lot of distributive property. So I'm going to distribute, and I get 4 plus 2i, and then I distribute plus 2i plus I squared. And I do the same on the bottom. Distribute, that's 4 plus 2i. And on the bottom, that's minus 2i minus I squared. The key to this whole problem is those two I terms cancel each other out. That's what's going to get the I off of the bottom. Other than that, we know I squared equals negative 1. And so negative I squared would be negative 1. So that's plus 1. I can clean up my like terms. On the top, 4 minus 1 is 3. On the bottom, 2i plus 2, still on the top, 2i plus 2i is 4i. And then on the bottom, I have 4 plus 1 is 5. Now, I like that answer. To me, that looks good. But if you're doing Math Excel, they're going to make you split the fraction. 3/5 plus 4/5 I. Both of those are the same thing. Both of those are correct. Next one, I-21. I feel like people didn't do so hot on this on the quiz. You have to remember that I, okay, we know I is like a square root of negative 1. And that's why I squared, when you square that, you get negative 1. I cubed is the opposite of I, and I to the 4th is negative 1 squared, that's positive 1. You want to kind of memorize those 4 things. Memorize them, or at least be able to figure them out, all right? And what you're going to do is you're going to try to figure out which one of those 4 things I to the 21st power is. And you know what you could do is you could extend this pattern and say something like I to the 5th is equal to I to the 4th times I. And we know I to the 4th is 1, so I to the 5th is just I. I to the 6th is I to the 4th times I squared. I to the 4th is 1. So we're at I squared, that's negative 1. All right, so what ends up happening, if you notice, I to the 7th is just going to be the same thing as I to the 3rd and I to the 8th. That's I to the 4th times I to the 4th. That's 1. Your pattern just repeats itself. You always go I, negative 1, negative I, positive 1. And then it just recycles over and over and over again. So if you wanted to, you could just count all the way up to 21 in this problem. But the easiest thing to do is to say, well, I know that every multiple of 4 is going to equal 1. And so what I would do is I would rewrite I to the 21st power as I to the 20th times I to the 1st, knowing that I to the 20th equals 1. Multiples of 4. 1 times I to the 1st is just going to be I. So I'm going to do another one of those because I know that students kind of struggle. So let's say we have I to the 34th power. I to the 34th power. So what is that? It's one of those 4 things. What I would do is I would say, well, there's a multiple of 4 nearby, that's 32. If you can find a multiple of 4 nearby, then this problem should be doable. We know that I to the 32nd power is equal to 1, so we're looking at 1 times I squared. But you've memorized that I squared is negative 1. 1 times I squared is negative 1. Distance and midpoint is going to be on there. And so I'll probably give you those formulas. The distance formula is square root of x2 minus x1 squared plus y2 minus y1 squared. And the midpoint formula is x1 plus x2 over 2 comma y1 plus y2 over 2. I shouldn't need to give you those formulas because it kind of makes common sense. If I'm finding the distance between those 2 points, according to the formula, you say x2 minus x1. So we've got the square root of x2 minus x1 squared plus y2 minus y1 and squared. All right, so negative 12 plus 19, that's going to be 7. We've got 7 squared plus 15 minus 12 is 3 squared. Looks like that. All right, that's 49 plus 9 is 58. We're talking about the square root of 58. All right, the square root of 58 might break down. It's kind of hard sometimes when you have to look at it. Square root of 58, can I break down to 58? One way, if you can't tell, is to divide by a prime number like 2. If you divide by 2, you get 29. That's prime. I don't have any perfect squares inside there. I can't break that down. And so that's my distance. That is my distance. And so the reason why I say this is kind of common sense, the way I like to look at it is I look at these 2 numbers and I say, well, what's the distance between those 2 numbers? If I graph those on a number line, they are 7 apart. And I don't really need to know the formula. I can just look at those numbers and say those 2 numbers are 3 apart. And so I can completely skip over the formula. I know it's distance squared plus distance squared right there. Anyway, midpoint. If you use the formula, you're going to say here's x1 and here's x2. So negative 19 plus negative 12 over 2. That's what, 21, 31? Negative 31 over 2. And y1 and y2, that's 12 plus 15 over 2. That's 27 over 2. Now, those numbers are kind of hard to do in your head, but if the numbers are easier, sometimes you can do that one in your head and just find what's in the middle. Find the middle. Graph the quadratic function and give a whole bunch of attributes. All right, so when we look at this quadratic function, the first thing I would do is find the vertex. So negative b over 2a. That's something you should probably have memorized. All right. in this problem, opposite of -2 over 2 times 1. That's going to be 2 over 2, that's 1. That is not the vertex. That is the x part of the vertex. To find the y part, you're going to plug in this number. So plug in 1, and we're going to have 1 squared minus 2 times 1 plus 4. That's 1 minus 2 plus 4, 3. There's a vertex at 1, 3, right there. All right. Now, if I have to graph this thing, if I have to graph it, I could make an XY table, but I don't want to. All right. I don't want to. I know that quadratic functions have this 1, 3, 5 pattern that we've talked about. It has to do with square numbers. If you go back and look at squares, where was that? Look at squares. All right. Now the first one was 1 and 0. Okay. If you look at the pattern that the square numbers make, +1. Wait, I did that wrong. Hang on. From 0 to 1 is +1. And from 1 to 4 is +3. And from 4 to 9 is +5. And from 9 to 16 is +7. There's this 1, 3, 5 pattern in the numbers that are perfect, in the perfect square numbers. And so I use that to my advantage when I graph. If I can find the vertex, I can use that 1, 3, 5 pattern. The only thing you have to look at is this number right here. All right, that's a multiplier. So if that coefficient is 1, I can just use 1, 3, 5 pattern. And what I mean by that is start your vertex and go up 1 and over 1. And then from that point, go up 3 and over 1. And from that point, you go up 5 and over 1. And so on and so on. You can go up 7, up 9, up whatever, okay? But usually by the time you get to 5, you're out of room anyway. So that's what my quadratic looks like. That's the easiest thing to do. Other than that, you can plug stuff in, but I don't want to do that. You know, finding the axis of symmetry is this line that goes right through the middle. Okay, axis of symmetry right there, and it's always going to match the x part. So the axis is x equals 1. And the domain, if I squash that graph onto the x-axis, it's going to end up covering everything. So the domain is all real numbers. The range is not going to be all real numbers. You squash that onto the y-axis, look at your minimum point. The minimum that graph reaches is right there at 3, just so happens to be this number. And it's going to go up. It's going to be everything from 3 to infinity. The interval of the domain for which the function is increasing and decreasing. All right, I know students have struggled with this before. So, you know, when it's increasing is right here. That's where the graph is increasing. And what people want to do is they want to say it's going from 3 up. And even though that's true, that's not how you answer this question. It wants the interval of the domain. All right, so you're always looking at the domain. If you squash that part onto the x-axis to look at the domain, that's what they're talking about. And so the increasing part of the domain is just going from 1 to infinity, the x part. The decreasing part of the domain is the other half of the graph. That's where it's decreasing from -infinity on the left to +1 on the right. Okay. Only other thing, somebody asks something about the Y-intercept. How do I find the Y-intercept? To find the Y-intercept, I'd plug in 0. But if you look at this equation, if you plug in 0, you're just going to end up getting this 4. All right, that's the Y-intercept, in case they ask. Y-intercept is 4, or the point 0.04. Toy rocket is launched from top of a building 76 feet tall at an initial velocity of 227 feet per second. Okay, so part A says give the function, and that function is going to look something like this. Y equals -16t squared plus the initial velocity 227t, and then plus the initial height, which is 76. It's going to look like that. I noticed on the quiz that I just graded, a lot of people like almost had it, but barely messed up. They missed a t, or they switched two of the numbers or whatever. But the negative 16 will always be negative 16 on Earth. And 227 is the velocity, and 76 is the initial height. So if you get that, you should be able to answer all of the other questions. Determine the time at which the rocket reaches its maximum height, and the maximum height in feet. Okay, so since this is a quadratic, t squared, x squared, you can kind of visualize what this graph is going to look like. It's a negative coefficient, so I know it's going to end up looking like this. That's what the graph looks like. It's an upside down parabola. And you can use a graphing calculator or a Desmos or something to graph that. That's probably going to be a good idea to do. So let's go ahead and do that real quick. So what was it? 227 and 76. One thing about Desmos, it does not like t's, so make sure you put x's. Oops. Like I said, make sure you put x's. So I'm going to check my numbers again. 227, 76. Okay, cool. Now, you can zoom, but it's still kind of hard to see. So I like to change this. Let's just make this -5 and 15. My y-axis needs to go up to, I don't know, probably 1,000 or so. Yeah, that's pretty good. All right, so if you change your axis, then it's going to show you what you need to show. So when they're talking about the maximum height, they're talking about the vertex, right? And so we can find the vertex on this graph just by clicking on it. I like Desmos a lot. And a lot of times we want this point, and a lot of times we want this point. So let's look at what they're asking here. Determine the time at which the rocket reaches its maximum height and the maximum height in feet. Well, they're talking about this point, right? And so the x-axis, remember I changed my t's into x's. Your x-axis is your t-axis. It's talking about time. And so the x number is talking about time. So it's going to take a little bit more than 7 seconds to reach this maximum height of 881.1 feet or whatever. Okay, so that would be your answer to that question. $7.1 seconds, is that right? 7.1 seconds and 881.1 feet. That symbol right there is the symbol for feet. Okay, so you can say that or FT. For what time interval will the rocket be more than 724 feet above the ground? So that one, more than, what did it say, 724? More than 724. Here's what I would do. Y equals 724. If you graph this horizontal line, you can see right there. This part of the graph is above 724. So when they ask this question, for what time interval, remember time is the x number. They're talking about the x number on this graph, between 3.96 and 10.2 or whatever. So between 3.96 and 10.23, let's say. So we would say and we're in interval notation. That is not an XY point. Just because I use parentheses, you've got to understand that that's an interval from this time to this time. After how many seconds will it hit the ground? will hit the ground. That's this point right here, right? The ground is 0. All right, so this is the time, 14.5. It's going to take 14.5 seconds for this thing to hit the ground. Now, if you weren't allowed to use Desmos, you'd have to, you could still do this without Desmos, because when we're talking about the maximum height, you're talking about the vertex. So basically, negative b over 2a will get you there, negative b over 2a and a calculator. For these other two, you're going to have to use the quadratic formula, all right? The quadratic formula. So let's take a look at that real quick. Let's see. I'm going to cheat a little bit here. So this was negative 16 and, shoot, I forget, 227.76. So this does plugs numbers into the quadratic equation, and you get, well, there's your 14.5, right? It gives you two solutions, negative 3.2 or negative 0.32 and 14.5. If you look back at Desmos, we ignored this point because you don't really care about negative time. Really, the time starts at 0. So we don't care about anything on this graph before this. But if you're just looking at the graph, yeah, that's where it hits the axis. And so that's one of the solutions, and that's one of the solutions. Now, if you wanted to answer that other question, what you need to do is set this equation equal to 724. You're going to end up having to, if you're going to solve, you're going to have to subtract that 724 over. And so it's going to involve 76 minus 724, negative 648. So I think what's going to happen is, if you set this equal to 724, subtracted it over because you want 0, we could just change this to, I forgot, what was it? 648. And we should get the same answer. Okay, 3.96 and 10.22. Yeah, there we go. Those are our two numbers. So it's the same thing. We don't really need Desmos, but man, Desmos makes it a lot easier. Factor into linear factors. So this seems more recent, given that k is a 0. All right. So I know some of you have had a hard time with factoring and what that means, but they're giving me one of the zeros. So that's a huge break. This is where we use that synthetic division. Add down and multiply, add down and multiply, add down and multiply, add down. Okay, great. We knew that was going to happen, though, because they told me it was going to happen when they told me that was one of the zeros. What's more important is we've just broken the problem down into an x squared. This is something that we should be able to factor. Factoring looks like this. I know that 3x squared must have come from 3x times x. As for the numbers, I need numbers that multiply to 35. There aren't very many possibilities. Those numbers do not add up to 16, but that's because one of them has to get multiplied by 3. So you have to kind of think about it, and you're like, well, if I multiply this by 3, that's 21. 21 minus 5 is going to be 16. There we go. Those two numbers are now going to multiply to negative 35, and they'll make that 16 when I multiply by 3. So just keep in mind how the distributive property works. Your 7 is getting multiplied by 3, so it has to be over there on the right. And so those are two of my factors. What I've noticed people always forget is this is one of your zeros, so that means that x minus 1 must have been one of your factors. Factor. The next one, list all possible rational zeros. This is a weird one. This is the one where we have to say the factors of 45 and the factors of 15. This one's kind of intense because we're going to have to take all those blue ones divided by all of those red ones. So I'm going to have 1, 1, 1, 1, 3, 3, 3, 3, 5, 5, 5, 5, 9, 9, 9, 9, 15, 15, 15, 15, 45, 45, 45, 45. Whew! I've got to take all the blue ones divided by all the red ones. So over 1, over 3, over 5, over 15. And now this one, over 1, over 3, over 5, over 15. Over 1, over 3, over 5, over 15. Over 1, over 3, over 5, over 15. And then I have, this problem is intense. There's a lot. Usually you don't have this many. Then I'm going to reduce. So this one's 1, okay, plus or minus 1. It's got to be plus or minus. And I've got 1/3 and 1/5 and 1/15. And then this one's 3, right? And this one's 1. I've already got that. And then we've got 3/5. And this one reduces to 1/5. I've already got that. Here's 5 and 5/3. That reduces to 1. I've already got it. That reduces to 1/3. I've already got it. And then 9. And then 3. I've already got it. And then 9/5. And then, what's that? 3/5. That's 3/5. I've already got that one. And 15. And that's 5. And that's 3. And that's 1, and then 45, and then that's 15, I've already got it, and that's 9, I've already got it, and that's 1/3, I've already got it. So, like I said, this one's kind of intense, but those are plus or minus all of those are the possible rational zeros. Okay, and what that means is when we look at a polynomial like this, we're expecting there to be 3 solutions. 3 real solutions or 3 rational solutions. If there are 3 rational solutions, they have to be in this list. All of those numbers will not work. Hopefully, 3 of them will. So then it says find all the rational zeros and then factor it. Okay. So this is like one of the hardest problems because we have to figure out something that works. Okay. I would try really hard not to do the fractions first. I would try to see if 1 works. And so that's where we have to do this. And it gets really frustrating when we can't find one that works. And these numbers are going to be hard to do. 15, add down, that's 68, 78, 178. That's 178. I can tell right now that's not going to work. Okay. Something else you can try that you may not have thought of is graphing, okay? Because we now know how the graph relates to the zeros. So let's try this on Desmos real quick. So get rid of that. And we're going to type in y equals 15x cubed plus 163x squared plus 257x plus 45. Okay, now, all right, check it out. The zeros are the x-intercepts. And so I can see that there's a 0 at -9. That means there's a factor of x plus 9. And I can see these other 2 are Desmos. And so that's a little bit harder to come by because they're fractions. All right. Negative 1.67 would be like what? 1 2/3. 1 2/3 is like 5/3. So we would have x plus 5/3. But that's not what I want. That's not what I want. That's not going to work. I would say 3x. Wait, what would that be? Divide by 3 plus 5. Solving that would give me negative 5/3. Okay. Likewise with the negative 0.2, that's like 1/5. I would not say x plus 1/5. Whatever number you're dividing by there has to go in the front. So I'd say 5x plus 1. That's still going to give me subtract 1. Whoops. Subtract 1, divide by 5. That's still going to give me the negative 0.2 that I need. Now don't forget the easy one, x plus 9. That's factored. Okay, find all rational zeros. Those are the rational zeros. I didn't write them down, but those are the rational zeros. Sounds like we're out of time. Okay. Next question. Find a polynomial of degree 3 with real coefficients and zeros at this, for which f of negative 2 equals 30. I think the first half of this problem is fairly simple. We're looking at 3 zeros. So you should be able to tell me that that corresponds with factors x plus 3, x plus 1, and x minus 4. You need to multiply all this out to find a polynomial. That's what they're after, a polynomial. So we can distribute. It's going to be x squared minus 4x plus 1x minus 4, x squared minus 3x minus 4. And then we're going to have to distribute again to get all that in there. So distribute x cubed minus 3x squared minus 4x plus 3x squared minus 9x minus 12. Like terms, x cubed, that cancels, so minus 13x minus 12. That is a polynomial, but that is not the final answer. That's really close. If you can get that far, you're really close. But we also have to consider this information. When you plug in negative 2, you're supposed to get 30. And I don't think that's going to be the case here. If I plug in negative 2, that's going to be negative 8 plus 26 minus 12. That is negative, that is 18 minus 12 is 6. When I plug in negative 2, I get 6. I'm supposed to get 30. So basically all we have to do is we say, well, I'm off by a factor of 5. If I just multiply by 5, I'll get to that 30 that I need. So f of negative 2 equals 6. I'm going to multiply by 5 and get 30, right? I'm going to multiply by 5. So all I have to do is take this polynomial, and I'm going to multiply it by 5. That's going to produce what I need. That's going to give me 5x cubed minus 65x minus 60. There's my polynomial. Polynomial with degree 3, and if you plug in negative 2, you're going to get 30. Find all complex zeros of the polynomial function, give exact values. When they say complex, that makes me think of imaginary. It makes me think that some of the zeros are going to have imaginary parts, like complex. When I think of complex, I think of something like 2 plus 3i. So let that be a hint to you if it says something about complex. When I look at this graph, I expect there to be 3 zeros. All right, let's look at what happens when I graph it on Desmos. Okay. All right. That, okay, check it out. When I look at this graph, I only see 1, 0. I see a 0 at -7. This one doesn't touch. So I don't have 3 x-intercepts. I only have 1 x-intercept, which is weird because we were expecting there to be 3 zeros. But that just goes back to the fact that some of the zeros are going to be complex. They're going to have imaginary parts. So of course you can't see them if they're imaginary. Now, one thing about Desmos is it helps me see the one that I know of. -7 is one of my zeros. So the first step on this problem a lot of the times is we've got to figure out what could possibly work. 1, 35, 5, and 7. This is a 1. So the possible numbers that could work are going to be plus or minus 1, 5, 7, and 35. Of course, we'd have to divide by this 1, but that just tells me that I don't have any fractions. And so looking at that graph from a minute ago, I know all of these numbers don't work, but according to the graph, I know -7 does work. So check out what happens when I do my synthetic division on a -7. Add down and multiply. Add down and multiply. Add down and multiply. Add down. Okay, good. I knew that was going to happen. Of course, it was going to happen because I could see on the graph that -7 was going to work. That's one of my zeros. There are 2 more. There are 2 more. They didn't show up in that picture because they're going to have imaginary parts. So we look at this, x squared plus 4x plus 5. And normally we could factor this. And so it's like x and x make x squared. I need numbers that multiply to 5 and add up to 4. And so it's common for people to say, well, 5 minus 1 is going to make 4, but a 5 and a -1 is going to make -5. I have to make a +5. And so the only way to make a +5 is if both of these are negative or both of these are positive, and you're not going to be able to do both things. You're not going to be able to find 2 numbers and multiply to +5 and also add up to +4, which means this can't be factored, which means this is going to be a nasty looking answer, okay? So if I can't factor it, maybe I can use quadratic formula. And so that's the thing where you go opposite of b plus or minus square root of b squared minus 4 times the a number times the c number all over 2 times a. And what I would do is 4 times 1 times 5 is 20. So I've got 16 minus 20 is -4 there. -4 plus or minus square root of -4 all over 2. Well, we can do the square root of -4. We know how to handle that. Square root of -4 is 2i. And so if I split the fraction, -4 over 2 plus or minus 2i over 2, I'm looking at 2 different answers. If I take the top branch, that's -2 plus I. And if I take the bottom branch, subtract, that's going to be -2 minus I. Those are my complex solutions. I've got 3 zeros. It's just those 3 zeros might be complex. -7, -2 plus I, and -2 minus I. Function defined by this polynomial has the graph as shown. Use the graph to factor the polynomial. I like this question. This is an interesting question to me. I see this 4 tells me there are probably going to be 4 solutions, but I look at the graph and I only see 3 x-intercepts. I see -5 and 0 and 2. But this is a problem where you want to think about multiplicities. Multiplicities. Since this thing bounces and looks like x squared here, that means a multiplicity of 2, or it's repeated. And this looks like a straight line, so that's just a multiplicity of 1, as is this multiplicity 1. I can tell a -5 with multiplicity 2 means that it's there twice, okay? It's a repeated 0. And then there's a 0, and then there's a 2. Those are my 4 solutions, right? And I know the first one is repeated, so technically there's only 3, but those are my 4. You want to find the factors. Well, x minus 5 comes from a factor of x plus 5. And so this one would as well. And 0 comes from a factor of just x. Think about it. We're trying to find what factor, in order to make that 0, 0 makes x 0. That's deceptively easy. And then 2 comes from a factor of x minus 2. Those are the factors. I would probably write the x first, and then I might squeeze the x plus 5 together and make a square. That's the factored form of that polynomial. All right. Next, graph the polynomial function, factor first if the expression is not in factored form. So if I need to factor this, I might find the zeros, 1 and 15, 3 and 5. I know Desmos will handle most of this. Your graphing calculator will handle most of this, but they want the zeros. We're looking at the zeros. So let's see what works. Let's see if 1 works. Oh, that's nice. It doesn't normally happen that I get it right on the first try, but I know 1 works. I know there's going to be a 0 at 1. I've broken down the problem into something that I can hopefully factor. 2 numbers that multiply to 15 and add up to 8 are 3 and 5. So that means there's a 0 at -3 and another one at -5. -3, -5, like that. Those are my zeros. They come from the factors, all right? Factor first if the expression is not in factored form. So again, if you have to factor it, factored form, that's coming from a factor of x minus 1. That's factored form. But factored form is good for finding those zeros, and the zeros are going to show up as the x-intercepts on the graph. Now, if I have to graph this polynomial, there's something else that helps, and it's called the end behavior. You look at the first term, and since that's a positive number and an odd power, you should know that a positive odd function is going to do this. And so I can kind of think about my function, the end behavior is going to look something like that. And we can do that now, or we can do that later. Other than that, I might just want to plug in some numbers and see what else the function does. A good number to plug in is something like 0, because when you plug in 0 into this function, everything falls out. You're left with -15. 0, -15. It's going to be probably right in here. Right? I might plug in a -4 just to try to see what happens. And oh, that looks like a tough one to do. Got -4 to the third plus 7 times -4 squared plus 7 times -4 minus 15 is 5. Plug in -4, get 5. Plug in -4, get 5. That's going to be like right there. That's probably good enough. That might not be perfect, but that's a decent idea of what that graph looks like. If you want more info, you're going to plug in like -2 and -1 and see more points. Using the intermediate value theorem, show that the function f has a 0 between a and b. This is something that you probably missed or you probably forgot. It's a very tiny little part of that lesson, but the intermediate value theorem, I bet you missed this. Okay, essentially what you want to do is plug in these two numbers. Plug in -5, and -4. And you can do it by synthetic division, or you can do it by just plugging it in. It doesn't really matter. So let's just plug in, because you probably understand plugging in better. -5 cubed plus 3 times -5 squared minus 9 times -5 minus 13 is -18. Okay, now I'm going to plug in -4. I get 7. Okay, so this is a hard concept to understand. Once you get it, you got it. So if I look at a graph and I go to 1, 2, 3, 4, 5. Here's -4 and here's -5. When I plug in -5, we got -18, which is going to be way down here somewhere. When I plug in -4, I'm going to get +7, which is up here somewhere. So when you think about this function, whatever the function is, whatever it does, it's going to have to connect those two dots right there. I don't know what the function is. I don't know what it does, but I know it connects those two dots. And so the intermediate value theorem just basically says if you connect those two dots, there must be a 0. Okay? So it's something like, since f of -5 is negative and f of -4 is positive, there must be a 0 between -5 and -4. Intermediate value theorem. Now we're going to talk about asymptotes. Give the equations of vertical, horizontal, or oblique asymptotes for the graph of this function. All right, I'm going to give you those formulas, but it doesn't hurt to be familiar with them. First thing you'd look at is vertical asymptotes in holes. Okay, look at where the bottom equals 0. If it cancels out, it's a hole. If it doesn't cancel out, it's a vertical asymptote. So in this case, doesn't cancel. That means we've got a vertical asymptote, x equals 1. All right? Now, horizontal or oblique has to do with the degrees of the top and the bottom. All right? There are no variables on the top, so that's going to be a degree 0, and the bottom is degree 1. When 0 is less than 1, when the degree of the top is less than the degree of the bottom, we know there's a horizontal asymptote at y equals 0. Right? That's something that's going to be on there. You're going to have to know that, and I know students kind of struggle. That's something that requires practice. So then the next question just says, let's graph this. All right, so if I'm going to graph that same thing, we just found a second ago that there's a vertical asymptote at x equal 1. And there is a horizontal asymptote at y equals 0. In the lesson, I gave you a whole bunch of steps to go through, and you can go through all that stuff, but the short of it is just start plugging stuff in. Okay, if all else fails, just start plugging stuff in. And it's almost always going to be a good idea to go just to the left and the right of the vertical asymptote. I don't want to plug in 1 because I'm going to get a 0 on the bottom of a fraction. That's undefined, so don't do that. But I might do 0 and 2. Those might be easy numbers to plug in. If I plug in 0, 4 over 0 minus 1, that's going to be -4. 0, -4. Notice my scale goes by 2's. And if I plug in 2, I've got 4 over 2 minus 1. That's going to be 4. 2, 4. 2, 4 is right there. Don't forget about the symmetry. You can do more points if you want to, but I'm pretty confident this thing's going to look like this. Now, they might ask you for domain and range. Domain of this, if you squash this onto the x-axis, we know it's going to cover everything except for that 1, this 1. So this is a complicated way of saying everything except 1. As for your range, it's going to be everything except 0. You're looking at this one for the domain and this one for the range. Your range is going to be everything except 0. Next, give me the asymptotes again. It's kind of weird that they switched this one around backwards, but I would rewrite this as negative 3x plus 3. We might need to factor. If I factor out a negative 3, that would give me x minus 1. And if I factor out a 2, that gives me x plus 1. I thought maybe something was going to cancel, but it doesn't cancel. And that makes a difference, right? Because it's a vertical asymptote if it does not cancel. You look at what's going to make 0. In this case, is negative 1. And if it cancels as a whole, if it doesn't cancel, it's a vertical asymptote. That's a vertical asymptote. Then you look at horizontal or oblique, and it has to do with the degree. The degree of the top is 1, and the degree of the bottom is also 1. When the degree of the top equals the degree of the bottom, that's when we have to do the leading coefficient over the leading coefficient. So in this case, the leading coefficient is negative 3 on the top and 2 on the bottom. Horizontal asymptote, y equals negative 3 over 2. Same question, give me the asymptotes. So again, if we could factor this on the top, maybe we could cancel something out, but I don't know how to factor that. You can't factor x squared minus 8. And so nothing factors, nothing's going to cancel. Negative 4 is bad news. And so since it does not cancel, we're talking about a vertical asymptote at negative 4. As for your horizontal or oblique, look at look at the degree. Degree 2 on the top, degree 1 on the bottom. If the top is 1 more than the bottom, that's going to be oblique or diagonal. That's going to be, this one's going to have a diagonal asymptote. And so that's where we're going to have to divide. We're going to have to actually do this division that it says in this problem. We're going to do that division. And the easiest way to do that is to think of it as a synthetic division problem. That's what that says, x squared minus 8. And we're not going to use the plus 4. We're going to use that 0 value, that negative 4. Add down and multiply, add down and multiply, add down. That's the remainder, but we can ignore the remainder. We just look at this part, x minus 4. X minus 4. And so we're going to have an oblique asymptote, y equals x minus 4.